thank you very much, Raul, for the introduction. First of all, I start with good morning to you all who are attending or connecting through this workshop from Europe, and also good afternoon or even good evening to those who are connecting from other side of the world, like myself from Australia. Right now it is dark here, 7 p.m. And also I would like to thank you, Professor Raul Fangario, for very kind invitation, and I'm hoping that we are going to have a very good discussion for the section. I would like to begin, a little bit about Deakin University and Institute Frontier that I come from, and I'm presenting the work that we have done there. Deakin University is a public technical and research university in Victoria, Australia. It has been founded in 1974, a relatively young university, but it has been ranked in top 2% of the world's university in academic ranking of World University. And so as you can see from this map here, Deakin is located in Victoria, the state in southeastern Australia. So we have 4 different campuses, one in Melbourne, one in Warrnambool, and 2 Geelong, which myself, I'm based on Warrenpoint campus in Geelong. The other campus is Warrenpoint campus, Waterfront campus. So I would like also invite you all, after the pandemic, everything is finished, come to Australia, Geelong, especially to visit Deakin and the beautiful city of Geelong, because it is very famous for the beautiful scenery and also international beaches for international surfing competition. So IFM, Institute for Frontier Materials, actually is located in 2 campuses of Deakin. One of them is in Warrenpoint campus, which, as I said, myself, I'm based on Warrenpoint. The other one is in Melbourne. So it is very much a multidisciplinary institute, I would say that, and there are different academic people with different background working on 5 major fields: advanced alloys, energy materials, carbon fiber and composite, infrastructure materials, and fiber and textile. So we have 150 HDR students, and every year there are 30 PhD students that complete the course. Majority of our students are based on Geelong Warrenpoint campus, and not only the institute is very multidisciplinary institute, but also it is very multinational, multicultural institute in terms of the number of students that we are having there, almost from 30 countries. Okay, so here I would like to start the topic with presenting this data from about global waste generation from economists to further emphasize that why this workshop like this and talks similar to this one are important. The economists actually reported that 2 billion tons of waste produced in 2016 and expected to be nearly doubled by 2015. Every single day, each man, woman, and child on this earth producing around 750 grams of waste, and 30 billion tons invisible carbon dioxide are dumped into the atmosphere every year. So in playing a very small part in tackling the associated problem with waste, I'm going to briefly talk about some of our projects that, they are still ongoing. And the main of all of these projects are redesigning waste for cleaner material production. Today, I will talk about adding value to cotton gin trash and how we have how we have gave this waste a new life in turning the complete trash to treasure. I would talk about a natural approach to dye acrylic fiber using alpaca fiber waste. And finally, I will talk a little bit about the green insulation for automotive industry. So I will start with cotton gin trash project and a little bit about the production of the cotton. So as you may know, cotton leads natural fiber production with almost 23% of total world fiber production. The worldwide cotton production is around 120 million bales per year, and more than 70 countries are producing cotton. Among all of those countries, Australia is not the main, producer of the cotton, but we are the main exporter of the cotton. Almost 2% of the world production of the cotton happening at Australia. For collecting and processing this cotton, this cotton needs to be clean, and the planet of the cotton is required to be harvested and going through the ginning process. So the ginning process is when cotton fiber are cleaned and separated from the plant. The outcome of the ginning, as you can see here, are bales of the cotton that goes for the spinning of yarn and fabric production. The other one is cotton seed that goes toward seed oil industry. And the last one is cotton gin trash. This is the complete waste from the ginning process. Depending the harvesting and picking methods, the amount of CGT production varies between 24 to 58%, which is huge considering the amount of cotton production worldwide. The loss in material value is very high. So the cost of handling and disposal of CGT is also very high. Common disposal of CGT are dumping, spreading, and combusting. Apart from the cost of disposal, we are facing another problem, and this is fire. Every now and then we hear some of the reports that the burning happening in the ginning, and there are lots of trash, burning, and so this adds more cost to the ginners. So what exactly is CGT? As you can see, that picture clearly shows that CGT is very complex material. This is, there are lots of burrs, sticks, woody parts, leaves, which all of them are tangled with the cotton fiber. Chemically, CGT is mainly a lignoscellulosic biomass, a combination of the cellulose, hemicellulose, and lignin. It is actually a very sustainable source of biomass, and when it is broken down, the resulting organic polymer can potentially be converted into the biodegradable material for a range of application. So the first thing that actually we did to add value to cotton gin trash was using the trash and redesign it for the new material was to convert it to fine powder by milling. At the time that when we started this project, there was very limited report on cotton gin trash or CGT and its usage in material production. So we started our journey by investigation of its property, ways of powder fabrication, and how fabricated particles can be used in some potential application. Through the cutting and mechanical milling, we studied the changes in physicochemical properties of the particles, including size, morphology, surface area, crystallinity, chemical structure. And So finally, what we achieved was, as you can see here, the volume-based particle size distribution showed a mixture of two normal distribution of the particle. So different stage of the milling process up to 4 hours reduced the size of particles from almost 150 to 6 micromillimeter. However, when we increased the milling time, we didn't see any changes in the powder size. So almost 5 hours of the milling was enough to produce very fine powders. So as you see in the SEM images, the coarse powder contains still some of the fibers of the CGT or cotton fiber, but with the production of the fine powders, almost what we see was the very small particles. So we investigated the crystallinity of the fiber. There wasn't any changes in the crystallinity of the cellulose, but surface area, as we expected, increased because once you increase the milling time, you have higher amount of finer fibers, and the finer powders, and the finer powders have higher surface area. The thermal stability also reduced slightly after 6 hours of the milling. So in the next step, we use CGT powder in fabrication of the bioplastic through casting method with adding polymer like polyvinyl alcohol and also plasticizer. We also coated the surface with the ethylene cellulose, and the resultant film is a flexible, water-resistant, semi-transparent bioplastic film, which can be used for the packaging application, which I will discuss the properties later on. For the fabrication of the film, we studied the effect of different plasticizer on physicochemical properties of the film. The plasticizer that we used was diethylene glycol, glycerol, and then, as I said, we coated the film with ethyl cellulose. And as you can see from the STM images, the plasticizer actually improved the adhesion of the CGT and PVA by reducing of the pore sizes and providing the smoother surfaces. Our investigation also showed that the resultant film has a very high UV resistant or UV protection factor, and that was because CGT has lignin, and we didn't do anything to separate lignin. Lignin was there, and the phenolic groups that is in CGT is responsible for having higher UV resistant. We tested mechanical properties, and we tested against LDPE, which is a plastic that's mostly used for the packaging application. And it shows that, the film that we have developed, they're having higher tensile strengths comparing to LDPE. The modulus is relatively identical with LDPE. And also testing in terms of the folding endurance, it is very, very much flexible. Film can be folded repeatedly at single point for more than 200 times. So all of the reason actually for this was, because all of these plasticizer could penetrate into the both amorphous and crystalline region of the CGT. Even though CGT is not water soluble, but its chemical structure is compatible with plasticizer. Plasticizer occupied intermolecular spaces inside the CGT structure and interrupted possible van der Waals and also hydrogen bonds among the CGT molecules. Therefore, we saw the reduction in overall rigidity of the material, and also enhancement in the flexibility. So, as I mentioned, we coated the film with ethyl cellulose, and ethyl cellulose is a biodegradable polymer that is usually used in medicine coating. So when it was applied on the surface, we saw that the water resistant against the drop of water enhanced, and that was because ethylene cellulose has a less polar groups and it's more resistant to water penetration. Therefore, the lower amount of hydrogen bonding limits the contraction of the ethyl cellulose with water. So we see, the less penetration of the water after the coating. For this sort of film, we were approached by a company that they manufacture nappies for babies. So they wanted actually, and they're very interested in the material that we develop, and they wanted to replace the polyethylene backsheet, which is a synthetic and usually is used as a backsheet in the nappies. So they wanted to replace it with a more sustainable material. So we tested our material against water resistant in prolonged time. And then we realized that, these materials are capable of holding water for at least 6 and 30 minutes, even though there was some absorption into the water, but water couldn't pass through the film. And, there wasn't any, by testing the water resistant, there wasn't any droplet into the pot, but it was absorbed by the whole film. One of the good thing about this material was the color changing. As you can see that in this picture, the color change, is happening in this film, and it was like a bonus for this application, because it can act as an indicator for the time for changing the nappies. Regarding this material, another company also reached out to us, and they were interested, in replacing the mulch, which are mostly synthetic, with something more sustainable and biodegradable. So we tested our material against for the biodegradation property, and as you can see here, it shows that, after 30 days, almost 25% of the weight is lost, and it is biodegradable. But the thing is that we still believe that this material can be degraded more in the actual weather, like a rain or a storm or something like that, because PVA is more prone to dissolve in the water and breaks down the film. Remember that I talked about the UV absorption or UV shielding property of this material. This can actually act as a bonus for mulch application for this film, and because it can extend the durability of mulch against UV radiation. So another application for the film fabricated from CGT is bioadsorption. So for removing the dye from wastewater. And this is because the CGT is a ligocellulose, and ligocellulose naturally they can absorb, absorb dye. So, but for this project and for this application, we didn't use any other polymers similar to what I explained before, like a polyvinyl alcohol, to be added to the CGT powder and make a film. But what we did was fabricating pure CGT film by dissolving fine and coarse particle of CGT, as I explained before, in formic acid in a very mild condition, and then converting it to a film again through casting method. The method that we actually developed through this project was very clean production of the film using entire CGT with no residual left. And the other thing was that we were able to collect or recycle all of the formic acid that can be again used for the similar procedure. So as you can see here, SEM images shows that how the effective ratio of CGT to formic acid could affect the structure of the absorbent film. The lower amount of this one, here is the CGT to formic acid ratio, as I mentioned here in the picture, and then. So what we realized that, the lower amount of formic acid produced film with higher absorbency, as shown here. And it was due to introduction of the OH rich group. So from the SEM images and also from the roughness evaluation, we found that the roughness and pores formed in the structure of the film could help dye absorption. We tested a film for absorption of the cationic, like methylene blue, which is very, very common dye for dyeing, textile, and other polymers as well. And then, as I mentioned before, increase in the hydrogen groups in CGT as a result of acid dissolution enhanced the negative potential on the surface and increase the dye adsorption. But due to negative charge on the surface of the film, this sort of absorbent are not ideal for anionic dyes. So therefore, what we did was coated the film with very small amount of chitosan, and because by providing a positive charges on the surface, anionic dyes also were able to be absorbed into the film. So based on the absorption capacity that we calculated, it shows that, for the ionic dye, the film can absorb up to 150 milligram of the dye, and also for the cationic dye, it's more than 200, which is very high for comparing to the raw CGT. So one of the benefits of using this film was that because unmodified and chitosan modified absorbent can absorb different kind of cationic and anionic dyes simultaneously, by using these two forms of the film, we were able to absorb all both cationic and anionic dyes and remove it from the wastewater. The other thing is that we were able to test the reusability of this material, and it shows that the film that we have produced can be reusable after dissolving. So it can, after dissolving for several times of the dye from this can again be used. So another benefit of using the film as or CGT film as an absorbent was that handling of absorbent in the film is much easier than powder itself. So through this part, so all of these results really show that how much CGT has potential for redesigning material that can add the value to a complete trash and really make it to the treasure. So another project I would like to discuss is that the way that we used alpaca waste to dye acrylic fiber. And so alpaca is animal fiber. Alpaca fiber is animal fibers. So why we chose alpaca waste? Because during the production of the alpaca fiber, if it is shearing of the animals, getting the fiber, or even after yarn production, or even after using the fabric, almost 20 to 30% of the mass, is wasted. Alpaca is very luxurious and expensive, and it has very much similar properties like to wool, with higher moisture properties comparing to cotton and other synthetic fibers. But one of the interesting things about alpaca is that it comes in 22 different shades of the color. So with the idea of having different colors from the waste, we thought that probably we can make a pigment out of this alpaca waste and use it for coloration of the synthetic fibers to reduce the amount of waste. So we try to actually close the loop. So we used waste alpaca, make it powder, combining with the acrylic polyacrylonitrile through the spinning, we were able to produce the fiber that comes in the color without using any further colorant. So, and because of the embedded colorant into the polymer, it shows that it can have a lower consumption of the water. It can, have enhance the flame resistance of the acrylic, and also it can improve the moisture property of the resultant composite fiber while we're using the complete waste in that project. So why we chose polyacrylonitrile to use as a as a composite for this application is that, as you may know, acrylic after polyester and nylon is the most used synthetic fiber, which has a lots of usage in apparel, furnishing, industrial scale. And for dyeing acrylic, mostly exhaustion method is used, and there is a lots of wastewater full of synthetic dyes and chemical which is discharged. Acrylic, because of its structure, it is very high flammable, and also it has a very poor moisture properties that somehow restrict its application. So again, similar to what we did with CGT, we firstly investigated the way that we can use alpaca waste by converting it into the powder and a small particle size. So it was done through 3-step powder fabrication, as you can see here. So we convert the alpaca waste into snippets, and then slurry and dry powder, and finally air-jet mill powder. And through all of this process, it shows that, finally we can achieve to 2.6 micrometer of the particle size, which this particle size is exactly in the range of the pigment. So you may know that pigment are dye stuff that usually they are used actually for coloring materials, including textile and plastic. So here, by powdering, we were able to produce alpaca pigment. Looking at the morphology of the powder, so alpaca fiber on the surface, it had a scale. After converting to the snippet, there was some scale still visible on the surface of the fiber, but after changing to the powder, spray dry powder or air-jet mill, there wasn't any visible visible scale. So it shows that, they all of the scale were moved. But we didn't see any chemical changes in alpaca powder, and all of those main peaks which shows the structure of the protein, like amide 1 and amide 2, were visible through chemical analysis that we did. So, as explained before, what we did was, after converting those alpaca waste into the powder or pigment, we mix it with the polyacrylonitrile solution, and through the wet spinning line, we were able to produce the composite fiber with different percentage of the alpaca, from 10% to even 30%, that, the composite fiber were completely in color and colorful. And the reason that, because we used alpaca in black color, so the resultant composite fiber was like a brownish color. So the line here that we use is this system is capable of spinning 1 liter of DOP solution and 3 kilometer of the filament in length. So this project can be easily scaled up, and then, because the spinning system also has different section, all of the changes in the chemical, for example, in the washing bath or drawing section or winding zoom, all of these can actually help to modify the properties of the fiber by changing all of these parameters through the wet spinning system. So looking at the SEM images of the resultant composite fiber, it shows that, control pan, it's has a very smooth surface, but striation as a result of stretching was observed on alpaca composite pan. Also, the cross section shows that the resultant fiber have almost circular shape. We tested the mechanical properties of the composite alpaca pan fiber, and it shows that by adding the alpaca, once you add the alpaca content to the fiber, the composite fiber shows lower amount of mechanical strengths, and this is just because this pigment of the alpaca act as a filler into the pan chain. So what we did, as I mentioned, through the changing the parameter of the spinning line, like changing the drawing ratio, coagulation bath temperature, or coagulation bath concentration, we could achieve to the composite fiber with higher amount of like a 30% of the alpaca, with higher amount of alpaca, but still the properties was similar to the one with lower amount of alpaca, which had the higher amount of or better mechanical properties. By looking at the crystallinity of those composite fiber, it shows that, by adding the percentage of the alpaca into the fiber, the crystallinity index decreased, but thermal stability enhanced. And the reason that the thermal stability increased by additional of alpaca was because polypeptide chain of alpaca and protein structure ties up the flexible chain of pan and restricted the easy movement of the pan. So that leads to increase or decomposition temperature of the alpaca pan. Because since the thermal stability of the composite pan enhanced, it also helped to enhance the flame resistant property of the alpaca pan composite fiber. And again, due to addition of the alpaca, because alpaca has more hydroxyl groups in the structure, it also enhanced the moisture properties of the resulting composite. Looking at the biodegradability of the material, addition of the alpaca pigment to the pan enhanced the biodegradation of the material, and the weight loss was much higher after 6 months when higher amount of alpaca was included in the fiber. So because from the start the aim was to color those composite fiber, we also tested the color properties of the resultant or composite fiber, and it shows that with the addition of alpaca, color strengths also enhanced. And the reason, and then washing fastness and light fastness rating also was very high for the composite fiber, and it was because all of those pigment were embedded into the chain of the pan, so it was very difficult to come out after washing. So that is what we saw, that high washing fastness for this material. So through this project, actually we introduced a new pathway in coloration of the synthetic acrylic by reducing the amount of chemicals and water consumption when using natural alpaca pigment. It also proved fibers with improved moisture and also fire redundancy properties, which is very good for the fabric production. So, and finally, I would like to talk about green insulation for automotive industry, the project that we did in collaboration with Ford Motor Company in using waste wool fiber for production of the insulators. Like other industry, automotive industry, including Ford Motor Company, they are looking for ways to produce environmentally sustainable and recyclable materials to meet the new regulation and customer desires. So the insulator that they used in their car, they are mostly made of synthetics and actually takes hundreds of years to degrade. So the insulator are used in different parts, such as door trim, back panel, engine compartment, and on the ceiling. So the idea was using wool and replace wool waste material instead of synthetic insulating material. So why we chose wool waste for that sort of purpose? By looking at the structure, chemical structure, and also surface structure of the wool, you can realize that how complex is this material. And because of the chemical structure of this material, wool has a very exceptional properties among natural and synthetic fiber. It is inherently flame retardant, which is great for automotive application. It is odor resistant, and it is luxuriously soft. And finally, and more importantly, thermally and acoustically, they are insulating material or fiber. So actually using wool as an insulator has been practiced before for the building, but that was the first time that we tried and put emphasis on using wool for the automotive application for the insulator. So what we did at the first step was to actually facilitate designing of the green wool-based insulating material and to do reverse engineer to find out and investigate the properties of the currently available commercial automotive insulator. So as you can see here, we investigated the properties of two insulator, one made of polyester and the other one made of cotton polyester. We investigated the structure of these two insulator and the effect of fiber type, fiber diameter, area density, thickness on sun absorption, and also thermal resistant properties of the insulators. Then based on all of these results and reverse engineering that we did, we fabricated non-woven materials from waste and virgin wool fibers through needle punching technique. We fabricated a variety of densities and thickness, layer structure of the non-woven, and then systematically compared them with the commercial materials. So by using impedance tube, we evaluated the sun absorption coefficient and noise reduction coefficient of fabricated material in both high frequency and low frequency, and then we compared them with the commercial insulating material. So, noise reduction coefficient is the percentage of the sound absorbed by material or the percentage of the sound that is not reflected into the room. So it was very crucial for us to know better, to better know our materials in terms of the sound absorption. So, and also what we did was, we also investigated, and to have a more compact structure, we have used a layer structure and also a thin layer of nonwoven polyester. The result showed us that the thin layer enhanced the sun absorption, and adding two layers was more beneficial than using one layer in each side of nonwoven, as the layer closer to the sound source could absorb more sounds or noises. So In investigation of the impact of thickness and area density, the result shows that they having higher area density or gram per square meter and also thickness can produce better sun absorption at low frequency, but we didn't see any significant effect of these two parameters, GSM and thickness, at higher frequency. And in addition to noise reduction, thermal resistant properties of the fabricated nonwoven material was also evaluated. As you can see that this graph here shows both noise reduction coefficient and thermal resistance of fabricated material with different GSM and two commercial insulating materials, polyester PET and CEL PET, these two commercial material. Among all of this material, a wool nonwoven insulator with 790 GSM showed the highest noise reduction coefficient and thermal resistance, which is much higher than those commercially available insulating material. So, and we saw actually similar patterns for both noise reduction coefficient and thermal resistance once we consider all of different parameters such as fiber diameter, thickness, and gram per square meter. We also tested our developed material against antibacterial and antifungal properties. And, it was very interesting to see that, the nonwoven material developed from wool showed somehow very identical antibacterial activity and also antifungal property to those commercial one. And these commercial, I believe that they are coated with with some polymers to be antifungal, antibacterial for the application in automotive. But the nonwoven material fabricated from wool show almost identical result to those material. We also tested the biodegradation of the nonwoven wool against those commercial one, and it shows that a great, nonwoven wool showed a greater biodegradation rate, almost 50%, comparing to the commercial synthetic insulating material. So in overall benefit, we were able to show the potential of wool waste in sun absorption and thermal resistance that were very much comparable with commercial products. So wool also showed that they has a more other benefit like a biodegradation or added antimicrobial or fungal properties as well. So through this study, actually, we've showed that waste natural wool fiber have a potential to be used as a green, lightweight, and sustainable material in automotive, while they can be qualified for reuse, recycle, and also reuse, recover purpose at the end of the life of a vehicle. And we are hoping that very soon for use there are developed material in some of their cars. Finally, I would like to close this talk with a quote from Albert Einstein, and it is, "We cannot solve our problem with the same thinking we used when we created them." And at the end, I would like to thank you, my collaborators, my team of postdocs and PhDs, and their hard work and dedication have made it possible to work on real problems and providing solution for better future. I also thank you all, and I'm happy to answer any question.
Okay, Maryam, thank you very much for your presentation. Very interesting. You are doing a great job there.
Thank you.
So we have some time for questions, and we are waiting for some questions from our participants. Anyway, this perhaps I can put the first question on this topic of the insulators using wool.
Yes.
It's very interesting because wool was always a very interesting fiber also for this type of applications. When you compare with the normal insulators being used in the automotive industry, did you look at because we know air is quite important, the air inside of structure is quite important for the performance in terms of insulation. Did you look at this, how the structure is made and fibers are interlaced so that these voids inside of the structure are...
Yes, we did. Actually, as I said, this project was funded by Ford. So, because they're very keen to use this sort of material, we went through a very long journey with them to test everything. And then you're right, once, wool, because of the curvature and the structure of wool, it is very easy to trap the air inside of the structure of wool fiber. And then we also realized that there is a very good relationship between air permeability of the material with sun absorption. So if we can trap more air inside the structure of the nonwoven material, we are also able to reduce the noise much higher. So there is a very, very good correlation between these two. So yes, we did test the air permeability. Yes.
So we have already some questions here from Edilyn Pereira Andrade. She's asking about the LCA, if you are intending of if you performed LCA life cycle analysis on your developments.
No, we have, life cycle analysis. We haven't done this, but we think that this is the part of work that Ford, will do that. No, we haven't done this.
Okay, so we have other question from Murugesh Babu, I believe from India. I know the colleague. So what is the dye absorption level of CGT on acrylics compared to cationic dyes?
What is
the absorption level of CGT on acrylics compared to cationic dyes? I believe is on the absorption level of cationic dyes on the
CGT.
Yes.
Okay. Is that, for the if from my memory, we had 200 milligram per gram of the CGT for cationic dye against 150 milligram per gram for anionic dye. So, it was the percentage of the absorbency for these two different types of the dye. So we tested methylene blue, and also we tested CI acid 25 as an anionic dye. Hopefully, I could understood the question, and I answered. It's clear the answer.
Okay, we have a comment, not a question, from Tao Yang.
Yes.
This is, he's saying that he did some research on acoustic properties of fibrous materials, and he's saying that cotton perhaps would be better than wool for that application. Do you have any?
For insulation?
Yes.
I don't believe that.
Yes,
the thing is that, okay, I'm come from Australia, wool is,
Yes,
Australia
you are defending all the time. Yeah,
and, my top favorite is wool. It's a very complex material. So
he's saying that is for acoustic. I'm sorry, perhaps I read wrong. Yeah, for acoustic. Yeah.
But still, I believe that, because of the structure, as I said, because of the curvature of wool structure, still I believe that, the noise reduction for wool is much higher comparing to cotton. But the thing is that once we are looking at the noise reduction of the material, we need to look at as I said, there is a lots of parameter involved with type of fiber is one thing, but at the same time, there is other parameters like a thickness or gram per square meter of the material that greatly would change the property of the fabricated material. So you may have still I believe that would much better in terms of the acoustic property has better value comparing to cotton. But based in changing the other parameter, you can get somehow similar or even result from other type of fibers.
Yeah, I guess you are right, because there are many factors involved in the performance of these fibrous materials, and the structure itself is playing a very important role, of course.
Fiber type is just one parameter, but there's still lots of other parameters for insulating material need to be considered.
Yes, of course. We have other question from Franz Lopez. Thank you for a good presentation. Are you evaluating a process production from economic point of view? That part of the economical point of view of this processing is always there.
So yes, we have done some price calculation for all of these materials that we have developed, including cotton gin trash. Because, for example, in terms of the cotton gin trash and the film manufacture from this material, cotton gin trash, the value of cotton gin trash itself is next to nothing. So jeaners are very much happy to pay you something that you can dispose all of those trash from there. So this is completely free, the raw material. But the fabrication process itself, there is some cost involved. But it's not that much that can hinder the final application of this material. And then again, for alpaca waste material, the process that we choose for the pan composite or alpaca composite was exactly similar to the method that industry uses. The wet spinning system is very well known system that is used for pan production, and what we have done is just embedding pigment into that dust solution, and then forming new fibers. So there is, the production, maybe there is I would say that there is some reduction in terms of the price of the production of the material, because we are dealing with some waste.
Okay. Thank you. We have two more questions. We don't have time for more, so for quick answers as well.
Okay, sure.
One from Inês Boutiques. Thank you for your great presentation. Did you use different washing baths in the production of alpaca fibers to understand what the impact of these baths on the mechanical properties of the fibers?
Washing baths, different. I don't know what is the different washing baths, but we consider using the standard methods for the washing, and the result is based on the SCM or standard method that we considered.
Okay. Other question from Arvinder Singh from NIT Jalandhar, Punjab, India. What was the range of particle distribution for CGT?
Okay, so we could achieve up to 6 micrometer of the fine fiber, but depends on the last material or final product. We didn't need that much fine fiber, even though some of them like a 20 or 30 micrometer in terms of the fine or coarse powder would enough to provide us a good feel for different application.
Okay, so that's it. We don't have more
Okay,
time
sure,
for more questions.
sure.
Thank you very much, Maryam. Again,
I really
nice to
thank
see
you.
you. Nice to hear from you, and
Thank
thank you
you.
very much for sharing what you are doing there. Okay,
Sure.
thank you.
Thank you.
Thank
Thank you
you.
so much.